Very good afternoon once again. So I suggest everyone should keep a calculator with you. So today we will solve one of the important problem. All right. In last class we have discussed types of the random variables. Let's glance them once again. There are two types of random variable: discrete random variable and continuous random variable. If the random variable takes on any value in a whole observation interval, called as a x is called as a continuous. For example, a noise voltage by the electronic amplifier has a continuous amplitude. Therefore, a sample space S of the noise voltage amplitude is continuous. Therefore, a random variable x has a continuous range of values. A random variable takes uncountable number of possible values. If that is the case, means such random variables are called as a continuous random variable. We will see what you mean by a discrete random variable. A random variable x is discrete. A random variable if x can take on only finite number of values in any finite observation interval. So here the values will not be a continuous. Instead, the values are obtained at any point of instant. A discrete random a discrete number of discrete values. They are not uncountable. Using any situation involving the finite, consider here Sx, here space, a sample space, real numbers are assigned, that is called here Sx. So it has xi elements where I will 2, 3, 1, 2, 3 and so on till n. Now is pi seen. What is pi here? A pi is a probability of each real number. So it is called as a probability mass function. We discussed it already. So the probability of each that is called as here the probability mass function. When the range of observation Sx contains only a discrete values, we say that x discrete random variable. So this set will not be having uncountable numbers. Instead, it is having countable numbers. That's why it is called as a discrete random variable. So it is nothing but a pi. Let us see here. What is pi here? The probability pi associated with the discrete random variable. It is called as a probability mass function. We discussed in the last class. So what is pi here? The pi is a probability associated with each discrete random variable. So that term is called as a probability mass function. When all the discrete observation in Sx are considered, their probability must sum to 1. In this case, P1, P2, P3, P4 and so on till Pn. If we add all these probability, that should be equal to 1. That is said here. So for pi varying from 1 to n, that should be equals to 1. So that is the property of a probability mass function. Now a cumulative distribution function of a random variable may be written as, this is the expression, you should keep this point in your mind. Capital F, a capital X, this X is a random variable, this X is an independent variable, this capital F indicates a cumulative distribution function, and it is defined as summation of a probability of each discrete random variable multiplied with a unit step function. Then a probability density function for a discrete random variable may be written as the same definition. Instead of a unit step function, a delta function is used. Instead of uppercase F, small case F is used. These two formula are very important as the problem's point of view. Keep this point in your mind. So a simple definition, a summation. So these two formulae are regarding a discrete random variables. A CDF of a discrete random variable, this is the expression. a PDF, a probability density function of a discrete random variable. This is the equation. Only difference is here the unit step function is used, here the delta function is used. Here the capital F is used, here the lowercase f is used here. That's the only difference. All right. So now the important discussion. Let us consider three important examples of a continuous random variable. We have seen what do you mean by random variable, which assigns the real numbers to the outcome of a sample space. A continuous. The meaning of this, we will find unaccountable probabilities. If that is the case, means we can say that it is a continuous random variable. We are considering three important examples for the continuous random variable. Those three are written here. Those three are written. The uniformly distributed, exponentially distributed random variable, a normalized Gaussian random variable. For all these three, we will get three important formula and three important graphs. 3 plus 3 total 6 graphs, and 6 graphs, 6 equations. One equation for CDF and another equation for PDF. Two equations here, two more equations here, two more equations here. Then total 6 equations, then total 6 graphs. One graph is CDF, another one is PDF. Two graphs for each random variables. Total 6 graphs, total 6 graphs and 6 equations. That should be remembered. They are very essential as the exam point of view. So I repeat here the three important examples of continuous random variables. First one is uniformly distributed random variable, exponential random variable, a normalized Gaussian random variable. All right. The first one, uniformly random variable. We'll see here two. What is this? Here it is Fy of y, Fy of y. What is the difference? The capital F is used here, the small lowercase f is used here. If capital F is used, it is nothing but a CDF. It is nothing but a CDF. And a small f is used here, it is nothing but a PDF. It is nothing but a PDF. And it is the graph called as a cumulative distribution function, and it is the graph called as a probability density function. These two graphs are nothing but uniformly distributed random variable. Uniformly distributed random variable. All right. So what is this? The two graphs are given. Along x-axis the variable y is taken, along the y-axis a CDF and PDFs are taken here. So it is the expression for probability density function. How to identify it? Because of this lowercase, a lower letter f. All right, it is the expression for CDF. It can be identified because here the uppercase f is used here, right? So I will explain how to write this equation. All right, first write the expression for cumulative distribution function. So here three limits are taken here. Minus infinity, I think here it is wrong. Here minus infinity to y1, this region. First consider this region. In this region the CDF is 0, that is written here. What is this value? This value is varying from minus infinity to y1, minus infinity to y1. Meaning of this is this region, a complete this region. In that region, what is the value? Here it is 0, right? Fine. All right. Next, in between y1 and y2, this region, y1 and y2. So it is the straight line expression. You can write equation for this linear line as y minus y1 divided by y2 minus y1. This is the expression for that line in the range of y1 to y2. Here the y is varying from y1 to y2. All right, then after y2 till infinity, what is this value? You can see here, you can observe what is this value here. It is +1, that is written here. All right, so what is the relationship between a CDF and PDF? A PDF, a probability density function, it is the differentiation of the cumulative distribution function. What is differentiation of 0? It is 0. What is differentiation of 1? It is 0. So we don't get a PDF when the y is varying from -infinity to y1, and if the y is greater than y2. These are the reasons. In all these reasons, the PDF will be 0 here. All right, then what is the PDF in between y1 and y2? So let us differentiate this one. What is differentiation of y? Here it is 1. What about these all things? All these things are here constants. So differentiation of this is 0. Then what as a result we will get only 1 divided by y2 minus y1. For this PDF, for this cumulative distribution function, this will be the probability density function. How we have obtained it? Just differentiate this. What is differentiation of this first term? It is differentiation of y is 1, then differentiation of y1 is a 0. Then what is this? 1 divided by y2 minus y1. It is a constant that is written as it is here. Other than this value, PDF will be 0 here. So this is what the complete explanation regarding informally distributed random variable. All right. So what are the property of this PDF? The first one, a PDF is always non-negative and area under the curve is 1. In this PDF, the area under the curve will be 1. A CDF is continuous. Yeah, it is continuous and non-decreasing, obviously, and it is 0, and it is 0 at the left side, and it is 1 at the right side. Is that right? It is 0 at the left and it is 1 on the right. Yeah, obviously. So it is what the left portion, and here it is what the right portion. It is value 1 and here it is value 0. That is said here. And the derivative of the CDF is exist. CDF, a derivative of the CDF is where except y is equals to y1 and y is equals to y2. All right. So you have to understand the meaning of a random variable, especially a continuous random variable, and for that this is the first example in for random variable. So fy, it is the cumulative distribution function and a corresponding probability density function, and here we have written cumulative distribution function and it has 3 value. It is 0, here the one expression, and here it is 1. Later we know this relation. The relationship between PDF and the CDF is a PDF is the differentiation of the CDF. Differentiation of is 0 0. Differentiation of 1 is constant is 0. Then differentiation of this term become 1 divided by y2 minus y1. That's you have to here. Just are given here, and this is what a slight mistake, and it is varying from -infinity to. Here it is varying from -infinity to y1. All right. We will see the next example for the continuous random variable, that is called as a exponential random variable here. So 2 graphs are given. It is CDF because of that capital F, and here it is a PDF because of a lowercase lowercase f here. Cumulative distribution function or probability density function. 2 graphs should be written under the exponential random variable. All right, let us write the expressions. For this graphical representation, a mathematical expression is written here. Cumulative distribution function and here this is the cumulative distribution function, and it is the probability density function, and this is the mathematical expression for this curve, right? Okay, and here the x is varying, and it is there only if x is greater than or equals to 0. All right, if x is less than 0, and it is 0 here. All right, so we do have a probability cumulative distribution function, then easily we can obtain a probability density function by differentiating this equation. So differentiate this equation, a differentiation of 1 is 0. So finally, let us we discuss its property. A PDF is always non-negative. Here we don't find any negative values here, and area under the curve is always 1. Here this area under the curve is always 1. Now a PDF is continuous and non-decreasing from 0 on the left and 1 on the right. It is continuous value here. It is there continuously, and 0 is existed at the left side and 1 is existed at the right side. That is said here. The derivative of the CDF exists everywhere except at x is equals to 0. Except at x equals to 0, the differentiation means a derivative of the CDF is existed. So these are the properties of the exponential random variable, and these are the waveforms for the exponential random variable and corresponding expressions. These two equations and these graphs and properties should be remembered as it is. Here the condition is this lambda should be it is called as a rate constant, and it must be greater than a 0. Okay, do one small correction, it should not be there. One expression for cumulative distribution function is 1 minus e to the power lambda x here. So if it is differentiated, we will get lambda into e to the power minus lambda x. Just do this correction, it should not be there. All right, so next type of a continuous random variable, it is called as a normalized Gaussian random variable. Keep these two graphs in your mind. You should keep 3 points in your mind. A variable y is used to represent the normalized, and for a normalized Gaussian random variable we must make use of a variable z here. Here the PDF, and here it is the CDF because capital F, and here it is lowercase f here, and these are the equations. It is the CDF and its corresponding a PDF. 1 by square root of 2 pi integration over minus infinity to z e to the power minus u square by 2 into du. Then if it is differentiated, definitely we will get this equation. If a differentiation is added here, what will happen? So what is this? D by dz of f of z is what? Fz of z. Then this differentiation and integrations will be cancelled. Apply d by dx here. What happens? This differentiation and integrations will be cancelled. What will get? Only 2 pi square root of 2 pi and this constant. Do not worry about z and u. They are only variables are changed here, but not the values. So differentiation of a CDF that gives a PDF here. So these equations should be remembered. It is called as a third examples for the continuous random variable, and you should keep these two graphs in your mind, right? Okay, so let us we discuss the properties of the Gaussian properties of a normalized Gaussian random variable. The first one, the PDF is always non-negative and area under the curve is 1. Area under the curve is 1. When z tends to infinity, in the formula, what is there? Actually, it was varying from minus infinity to z. The condition when z tends to infinity, what happens here? Let us see. It is the cumulative distribution function where z is replaced by infinity, and that gives the value 1. Why? Because we know that integration over the limit minus infinity to plus infinity e to the power minus z square by z into dz is nothing but square root of 2 pi. It is the definition of a gamma function. I think you might have studied it. What is that? So if z tends to infinity, this complete term can be replaced as square root of a 2 pi because it is the definition of a gamma function. So in the numerator square root of 2 pi, in the denominator already square root of 2 pi is there, then they do cancel each other, then we will get 1. So this equation, and when z is infinity, then obviously it can be replaced by a value 1. Keep that point here. It is one of the important definition here. Then the second property, a CDF is continuous and non-decreasing from 0 on the left and 1 on the right. Same thing is happening here. Then the derivative of the CDF exists everywhere. So these are the definitions, graphs, and equations for the continuous random variable. So one of the important discussion here, I will repeat, 3 important examples of the continuous random variable: informally distributed, exponentially distributed, then normalized Gaussian random variable. The first one, we should make use of a variable x. Then these two are the graphs and corresponding equations and 3 properties. Then second one, exponential random variable, 2 graphs and 2 equations and 3 properties. And the third one, a normalized Gaussian variable, 2 graphs, 2 equations and 3 properties. And here in a normalized Gaussian variable, random variable, you should make use of a gamma function definition here. When z tends to infinity, the CDF gives the value of 1 here.